Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about another iteration method. I'm kidding. Why did I say iteration method? Another method for computing x equals b, and that's the gradient descent. Yeah, so previously we talked about, well, two different methods for computing ax equals b, and that's direct methods and iterative methods, right? So you can check that out in my previous videos in my scientific computing playlist. So maybe we can have a brief recap. So for our direct solution methods, mainly we talked about Gaussian elimination. Um, yeah, we talked about Gaussian elimination and how we can use that technique to compute for the needed solutions based on some matrix A, vector X, and vector B. And we realized here that its computational complexity in big O notation is NQ, which is quite slow, if we're being honest. Um, and so we decided to talk about another algorithm or another way or technique for computing AX equals B, which is using an LU decomposition or factorization. And apparently, when we do this, we decompose A into two matrices, mainly a lower triangular and upper triangular matrix. And its computational complexity has been brought down to O of n squared, which is significantly lower compared to just using the Gaussian elimination algorithm. So we realized here that, okay, um, in some scenarios, or in most cases, in most scenarios, then we might as well use LU decomposition instead of Gaussian elimination. Um, so that's the idea there. Anything else? Yeah, so that's it for direct methods. And we also talked about iterative methods, which is this idea of starting with an initial guess, right? And as we iterate, or as we continue to increase our k, right, or our iteration, then we will converge to a solution, or we will get closer and closer to a solution. Um, so yeah, this is another way of solving ax equals b besides the direct methods. And in some cases, this is effective, right? So we introduce this Jacobi iteration scheme where we isolate x, y, and z right here. And then we attempted to solve this iteratively, right? So here we find the next x, y, and z value based on the initial x, y, z value, right? Because this is k, and we're trying to find k plus 1. So that's the Jacobi iteration scheme. And we get closer and closer to our desired solution. So this is the table, right? And as we go through says here the 19th iteration, we will get closer to a solution. What else? And we can, and then we introduce this concept of a matrix being strictly diagonally dominant. And so if it is diagonally dominant, meaning the sum of the absolute values of the off-diagonal terms is less than the absolute value of the diagonal term, well, then it's a dominant matrix A, diagonal dominant matrix A, which means it will definitely converge 100%. So that's the crucial thing we learned here. And then we introduced ourselves with a modification of the Jacobi iteration scheme, which is the Gauss-Seidel. And basically, to shorten it, the bottom line is, yeah, it converges to a solution in half the number of iterations. I didn't include the table here anymore, but pretty sure this was 10 iterations to get to the same solution as when we used Jacobi. The Jacobi reached 19. So this one only reached 10, which is about half. So this is definitely faster. And then from there, there's actually another way to compute for AX equals B. And here's what we're going to be talking about in this video. So that was a long disclaimer, which is gradient descent. So to start off, the Jacobi and Gauss-Seidel iteration schemes, right, the two, are actually only two potential iteration schemes that can be developed for solving AX equals B. But when it comes to high performance computing and solving extremely large systems of equations, then we need more efficient algorithms to overcome the computational costs of methods discussed so far. So in fact, modern iterative techniques are perhaps the most critical algorithms developed to date for solving large systems, which would otherwise be computationally intractable. So in this section, the gradient descent or steepest descent algorithm is developed. It illustrates how one might engineer an algorithm that continually looks to iterate in an efficient and intuitive manner towards the solution of the linear problem AX equals B. Moreover, it hints at the kind of underlying algorithms and techniques that dominate many high-performance computing applications today, including I'm not sure about this, the biconjugate gradient descent method, or the big stab, and generalized method of residuals. Okay, so to begin, we will consider the concept of the quadratic form. So this is the quadratic form. It's in the form of a function, actually. So it's a function which is equal to 1/2 of x transpose. So I'm assuming here x is a vector. Oh, it is. Okay. And we transpose that. So from a column vector, it becomes a row vector. We have A, which is a matrix. X is a vector minus B transpose. So B is another vector, X. Now C here is a scalar. Okay, let me just say that. A is a matrix. B and X are vectors, right? And C is a scalar constant. So it's just a number. And what? C is a scalar constant. Cool. Okay. Here we note that the quadratic form produces a scalar value f of x. So this actually gives us a number for our f of x. Okay. So that's the quadratic form. Don't know why it's called a quadratic form, actually, if I'm going to be honest, because from what I know, a quadratic form is a polynomial to the second degree. But here it's just about, I don't know, I haven't studied linear algebra. Maybe something to do with transposing a vector or something like that. Anyways, so the gradient of the quadratic form is defined as, okay, let's see. So it's can we put this little triangle here to signify it's a gradient? We put an equal sign, I believe. Okay, then we keep going. So this is actually, we're looking into partial derivatives here. So it's another concept. So partial derivatives is still a derivative. It's calculus. The only difference is that you have two variables to work with instead of single variables. That's what partial derivative is. Okay. So this goes to x2, derivative of the all the way to n. So this goes all the way to n. And so the gradient is a standard quantity from vector calculus that produces a vector field that points in the direction of greatest increase of the function f of x. So let me actually write that down. That's important. So the gradient, so this is the definition, is okay, let me not say vector calculus. Produces some sort of vector field that points in the direction of greatest increase of function f of x. So it's a vector field and it points in the direction of greatest increase of function f of x. We'll see exactly what that means in a while. So for instance, the quadratic form. So we can easily compute that apparently. Let's let's just follow what's being. So the gradient of the function from here, the quadratic form, can be computed easily. So here's the notation for that. There's like a triangle there that signifies we're getting the gradient. 1/2. Oh, okay. So they changed it a bit. So we transpose matrix A, vector x plus 1/2 ax. What do we notice? Well, oops, minus b. So from this function, we got to here. Um, I think I have an idea what happened, but I'm not confident. Actually, I don't know what the hmm. Okay. So if matrix A is symmetric, then the transpose of it is just equal to itself. And the gradient has a critical point, maximum or minimum, when its gradient is equal to 0. So this is something of a calculus thing. Kind of similar to getting the derivative. But yeah, what else? Thus the okay, let me actually try to dissect this. Gradient descent. Or let's talk about gradient first before descending. um, for gradient descent, What does this mean? It's the okay, so it's the standard quadratic form. Um, and to get the gradient, when I get the gradient of that function, do I just take derivative maybe? Not super sure if that's the idea. Oh, so I'm taking the vector of partial derivatives. So it's a multivariable derivative. Okay. Oh, so it actually tells us how to compute this thing. Um, cool, cool. Uh, yeah. So it's something about, oh, okay, okay. Yeah, it's something about computing partial derivatives to get the gradient, which I haven't learned yet. Um, but yeah, it's computing the gradient. So that's interesting. Yeah. Okay. So a couple of things for me to work on, maybe partial derivatives, so that I can actually compute, and it will lead to this. So right now I'm gonna take it as it is, but sooner I'm going to actually dive deep into what exactly how exactly to compute that. Or actually, I can try to do that now. Then how do you do that? Oh, when A is not symmetric. Huh. So here's when A is not symmetric. Hmm. Yeah, so this one is okay. That's interesting. Okay. So if matrix A is symmetric, then its transpose is just equal to itself, right? And we'll basically get AX minus B. Because if this was A, right? One half AX plus one half AX, well, we would just get AX. Then that's AX minus B. Also, okay, here we go. And the gradient has a critical point. So something about calculus. So a critical point, meaning, okay, meaning there's either a maximum or a minimum. Okay, when it's gradient, when the gradient of my function, I'm assuming this is a function, is exactly zero, and AX is equal to B, right? So the solution works. So I'm saying the gradient is exactly my solution, right? Which is zero. I just added B. So the solution Actually, we just answered it. The solution to AX equals B is actually these critical points. Is a critical point of the gradient. That's actually the key of it. That's a key, or yeah, that's key. That's important. If in addition the matrix A is positive definite, so a lot of wording here. If matrix A is what we call a positive definite, what does that mean? Well, it just means that it's A transpose times its vector is greater than 0. Then the solution is a minimum. And I think it's vice versa. So it's a minimum of my function. So these observations concerning positive definite and symmetric matrices are critical in the development of the gradient descent technique. That is a technique that will try to take advantage of knowing the greatest direction of increase or decrease of the quadratic form. If A is not symmetric, then the gradient descent algorithm finds the solution to the previous linear system. So if it's not symmetric, it finds the solution to this thing. So this is not symmetric. Let me just write it. If my transpose is not equal to my original, right? So that's another key fact to remember. To develop an intuitive feel. So here I'm really just focusing more on intuition, not necessarily the math. To develop an intuitive feel for the gradient descent technique and the importance of positive definite matrices. Okay, let's do an example. So here, this matrix, we're going to say it's a positive definite. So it has a minimum. Its solution is a minimum. And it's symmetric. So, what does it mean again if it's symmetric? Pretty sure I wrote it. If it's symmetric, then its transpose is just equal to itself. And it has a critical point. Okay. So here we say we have a matrix A. And this has 3, 2, 2, 6. So it's a 2 by 2 matrix. We have a vector here. This vector is a 2 by 1 in dimensions. And we have a scalar here that's 0. And so with this example, A and B, solving for x is a fairly trivial exercise, which yields the solution. So it's actually, let's just say what it is. So my x vector is actually just some x1 and some x2. So this is a row vector because it's transposed. And so this is 2, -2. It's a row vector again because it's transposed. Right? Yeah. I can solve this using regular algebra stuff, but yeah, might as well let the textbook do it. So our objective is to develop an iterative scheme. So we're using iteration techniques, which moves towards this solution in an efficient manner, given an initial guess. So first we calculate the quadratic form for this case to be Okay, let me just quickly write that out. So, okay, so here we want to develop an iterative scheme towards this solution. So 2 and -2, right? Okay, so let's do that. So first we calculate the quadratic form. Let me write that out. So we're actually just using the formula that we have. So we have f of x is equal to 1/2 of my x transpose, right? My x transpose. So some x value, x1, x2 transpose. I'm just completing the whole thing. My a vector, so 3, 2, 2, 6. Yeah, my a vector times my column vector of x. So some x1, some x2. And I'm going to subtract that, right? To my, okay, there's another vector here. To my b vector, my b transpose. That's why it's a row vector. Times my x. So my x is again a column vector in this case. X1, x2. Okay, this is long. Oh. Okay. Let me continue. Oh no, that's it. Right? Yeah, because my scalar c is just 0, so I don't need the. Okay, so this is just effectively 1/2. Or well, let's try solving it already. Let's make it into algebra. So 3/2. X1 x1 squared plus 2x x1 x2. Yeah, here I'm multiplying the plus. Okay, plus 3 x2 squared minus 2 x1 plus 8 x squared. X sub 2. Yeah, I just evaluated these. I turned them all into algebra. Okay. What else? Now what? So now I get my gradient. My gradient is, what's my gradient? Well, now I have two things here, right? So I have 3x 3x1 plus 2x2 minus 2. Okay. Don't know where. Yeah, something about computing. Oh, I computed the derivative. I think. Not super sure where that came from. Uh, yeah, it's something about computing partial derivatives. Yeah, 2x1 plus 6x2 plus 8. Okay, Um, so okay, we have a figure here. It shows the quadratic form surface f of x along with its contour plot and gradient. The solution to ax equals b is shown. Okay, let me just show exactly what that is. Okay, let me show. So here's the figure for this. So we can see exactly where it is. There. So if we were to code this up, it should look something like this. So here we can see that we have a contour plot and its gradient. So the solution to ax equals b is shown as the circle at x equals its transpose, right? Yeah, so it's actually just these two. There's my solution. See here how it's a minimum because it's symmetric. Um, as a result of the matrix being positive definite, the surface is seen to be a paraboloid whose minimum is at the desired solution. So it is kind of like a paraboloid, right? Kind of like a paraboloid. Thus, the idea will be to construct an algorithm that marches to the bottom of the paraboloid in an efficient manner, right? So how do we get to this solution as quickly as we can? If the matrix is not positive definite, then the gradient algorithm is unlikely to work. Um, okay, we have another, wait, there was another figure here. Huh, figure two. Oh, okay. And I'm also going to show figure two. Okay, there's another thing I have to show here. Um, okay. So, well, here what this is saying. Okay, let me zoom out a bit. Okay. So here what it's saying is that in that figure, there are four examples that are important to consider. A positive definite matrix. So this this thing here, because it has a minimum. A negative definite matrix. So it's this one. An indefinite saddle matrix. Well, yeah, we can say it kind of looks like a saddle. And lastly, a singular matrix. So for the negative definite matrix, the gradient descent algorithm would fall away from the maximum point. Similarly, for the saddle or singular matrix. So here there's a maximum, right? Here there are maximums. Here I think it's a minimum. I think it's somewhere here. I'm not super sure. But we can tell there's definitely a minimum here. There's a minimum here. Um, yeah, somewhere along those lines. So for the saddle or singular matrix, the algorithm would either converge to a line of solutions, singular case, or drop away along the saddle. So given this graphical interpretation of the gradient descent algorithm, one can see how it may generalize to higher dimensions and larger systems. So in particular, for a high-dimensional system, one would construct a hyperparaboloid for a positive definite matrix where the algorithm would, okay, the textbook kind of stopped there, would force in an optimal way the solution to the bottom of the paraboloid and the solution. So the positive definite restriction is similar to the Jacobi algorithm, only being guaranteed to work for strictly diagonal dominant matrices. So, okay, just to recap, um, this is just an intuitive way of finding gradients, how they work, how does the algorithm work in 3D. something about derivatives in this case. Well, yeah, partial derivatives. And here we can say that the positive definite restriction. So when we look at the positive definite case, right? The Jacobi, this is similar to the Jacobi algorithm. It's only guaranteed to work for strictly diagonal dominant matrices. And so to build an algorithm that takes advantage of the gradient, an initial guess is first given and the gradient is computed, right? And this gives the steepest descent towards the minimum point of f of x. So that is the minimum is located in the direction given by negative of its gradient. So note that the gradient does not point at the minimum, but rather gives the steepest path for minimizing f of x. Okay, let me, oof. Okay, a lot of stuff here to, there's a lot of wording. Okay, let me just go through some of them. So we actually use this iteration scheme, iterative methods, to compute for its gradient, right? And we want to find the minimal or the optimal path towards getting that gradient, towards getting that minimum or maximum point. Okay, rather the steepest path. Yeah. Okay, so the geometry of the steepest descent suggests the construction of an algorithm whereby the next point of iteration is picked by following the steepest descent. Okay, so here's the function that will help us find the next point of iteration. So we say the next point of iteration is picked by following the steepest descent. So we actually look at this. So that function, its tau is equal to x minus its tau times the gradient of that function. So what does that mean? The parameter tau, so that looking t, dictates how far to move along the gradient descent curve. So in gradient descent, it is crucial to determine when this bottom is reached so that the algorithm is always going downhill in the most fastest and optimal way. So this requires the determination of the correct value of tau in the algorithm, right? So there's something crucial about this tau here. We need to pick the right one. So tau dictates how far to move along the gradient descent curve, right? So if we pick tau, if we pick a big tau, we'll probably step over the minimum or maximum, right? If we pick a very, very small tau, we'll probably take too long before reaching the minimum. So we have to pick a right tau. And how do we do that? Well, okay, so to determine or to compute uh, tau, well, we consider the construction of a new function. So now we make a new function just for tau. So we make a function where we plug in some tau, and okay, so it's this e-looking thing. So we actually put this thing in a function that will help us determine what tau. So we'll actually use this. So now we have a composite function here. And this one now must be minimized, right, as a function of tau. So this is something about derivatives. So we must minimize this to find the most optimal tau. So let's just do that. And so how do we do that? Well, if we want to minimize, we want to compute its derivative, right? So we actually do a partial derivative here of my function with respect to tau. And here I get, so it's a minimum. So I get the negative of the gradient. So I have my function here, where I plug in my function in terms of tau. And I actually, okay, and I multiply it by its gradient, which I'm assuming is some chain rule or something. I'm not sure how it goes underneath the hood yet. I have to study partial derivatives to really understand this. And matrix calculus. So the geometrical interpretation of this result is the following. Well, here, okay, let me just, so this is essentially gradient direction. So where is it going? Right? Off current iteration point. And this one, where I plug in my function in terms of tau, well, this is now my gradient direction of the future point. So there is some math to be able to get the most optimal tau here. And thus tau is chosen so that the two gradient directions are orthogonal or perpendicular. Yeah. So there is some code here, which I'm not gonna. I'm actually gonna show. Oh, okay. Gradient descent algorithm applies to the function. Contours are plotted for each successive value xy. Given the initial guess xy, for A, the optimal tau value is calculated, is orthogonal to the previous step. In B, a prescribed value of tau equals 0.1 is used. Okay, I'll just skip that part. But yeah, so to summarize, basically, we can use a gradient descent algorithm to find a solution of Ax equals B for the values of tau, right? And apparently this algorithm converges quickly. 11 iterations are required, so that's pretty quick, to the correct value of x. Note that if a simply radially symmetric function is considered, then the gradient descent converges in a single iteration. So in one iteration, we'll get to the solution, since the gradient descent would point directly at the minimum. This figure assumes a line search algorithm to find an optimal value of tau. In particular, the value of tau here is optimal in the sense that a given line search is conducted so that the minimum of the gradient direction is picked at the next iteration point. So there's some derivatives and iteration scheme going on here. So however, this is not a requirement. In fact, one can simply choose a fixed value of tau for stepping forward along the gradient direction. So okay, let's not talk about figures. Yeah, if we pick a small value for tau, we'll converge, yeah, but at a much slower rate. So such a method may be favorable in a case where the steepest descent algorithm zigzags a large amount in trying to make the projective steps orthogonal. This can happen in cases where long valley type structures exist in the function we are trying to minimize. Yeah, gradient descent is the first example of how to use a quadratic form along with a derivate gradient for building an iterative scheme for solving ax equals b. It can also be used as the basis for an optimization routine. As might be guessed, there are a myriad of improvements to such a scheme. Indeed, the gradient descent algorithm is the core algorithm of advanced iterative solvers, such as the biconjugate gradient descent method. Yeah, basically it's the basic algorithm. But yeah, pretty much the idea here is it makes use of derivatives to find a minimum tau in order to get as close as possible to the minimum or maximum, which is the solution to ax equals b. So that's pretty much so here what I'm trying to do, at least for gradient descent algorithms, is I'm trying to make it intuitive. It's the intuition that matters. So I mean, let's say, okay, if we were to go here, right? If we pick a really low tau, we could go like there. Now we're at this point. Then we could go there. Now we're at this point. If I can only zoom in, you might see the arrows. And if I could go here, right? If we pick a very big tau though, let's say from this point or from this point, oh, we could go beyond. So let's say this is going towards this point, right? All arrows are pointing towards this point. If I pick a very large tau, it could go beyond, right? It kind of scales that vector. So you want to optimize tau as well. You want it to be the right tau until you reach that solution. And it uses iterations in order to do that because you keep on going through this, I don't know, this plane, this surface, in order to get the accurate solution. And yeah, there's some math here. It uses apparently partial derivatives and matrix calculus. Yeah. So really my goal here is just the intuition, not necessarily the math, because I'm still taking an intro course. But yeah, I hope that helps. Really excited to see how this applies to machine learning, because I've heard they use some of these algorithms for training their models and such. So yeah, I hope you guys enjoyed. I hope this gave an intuitive definition of what gradient is. And yeah, I'll see you guys in the next one.